Welcome to Writing Chemical Formulas. Today we're going to work on being able to write chemical formulas and identify chemical formulas by name. First thing we need to decide when we look at a chemical formula is what type of bond it is. Now there are two types of bonds. There's ionic and covalent bonds. Ionic bonds are bonds between metals and nonmetals. So metals would be iron, sodium, magnesium. Nonmetals would be oxygen, chlorine, fluorine. When metals and nonmetals bond, the metal will actually give its electron or electrons, depending on how many it can give up, to the nonmetal, and the nonmetal will accept them and put it in its valence electron shell. Once that happens, we've created two ions. A positive cation, which is the metal, and the negative anion, which is the nonmetal. Because they both have charges on them, positive and negative, they're like tiny little magnets that stick together. Really strong, tiny little magnets. Covalent bonds are bonds between two nonmetals. So carbon and oxygen can form covalent bonds. We can have carbon monoxide and carbon dioxide, and they're going to share the electron. The electron will spend some time around the carbon, some time around the oxygen. We're going to look at ionic compound formulas first. They must have a balanced charge. That is the key to writing these formulas out. We have to have the same number of pluses or positive charges as we do the negatives. So the number of plus must equal the number of minus. The number of positives has to equal the number of number of positives has to equal the number of negatives. That is because we are transferring electrons. We can't lose track of those electrons. The positives and negatives help us keep track of where the electrons are going. So it has to be neutral for the overall charge of the compound. If we add the positives and negatives together, it will come out to 0. If we have two positives and two negatives, we add them together, we get 0. If we have two positives and one negative, we need another negative. In order to get that negative, we're going to change the number called the subscript at the bottom. It's like an exponent, but it's at the bottom of the letter. And it goes behind the letter that you want more of. And it represents the number of cations or anions. It helps us keep track of how many atoms we need to balance out the charges, to balance out the electrons and keep track of the electrons. An example of this is potassium combines with chlorine to make potassium chloride. Very common salt. To start solving this problem and write the formula for potassium chloride, we have to figure out the symbol for potassium and the symbol for chloride. Remember, chloride is the anion of chlorine. Whenever we form anions, we drop the ending and add IDE, so chlorine becomes chloride. So we're going to look potassium up on the periodic table. We will find it as a K. And we'll look up chlorine. It's Cl. Once you have found those, write them down. Potassium K, chlorine Cl. Step 2 is going to be to identify the charge on each atom when it forms its ion. So we're going to look up the charges on the periodic table. We find potassium with the red square around it, number 19. It is going to give up one electron. It's in the first column, has one valence electron to give up. Metals are always going to give up electrons. So everything on the metal side of the periodic table is going to give up electrons. Nonmetals are going to accept them. So chlorine is going to accept the electron from potassium. The question is, how many of each do we need? Chlorine is in the 7th column, Seventh group, 1, 2, 3, 4, 5, 6, 7. It wants to be at 8, so it looks like the noble gases. They're the cool guys in the periodic table. Everybody wants to look like the cool kids. So these are the cool elements. Chlorine needs to gain an electron, but only one electron. If it gains 2, it's going to have too many. It's not going to have 8. We call this rule of 8 the octet rule. So, now we've decided that chlorine wants to gain 1 electron, potassium wants to lose 1 electron. When potassium loses its electron, it's going to form a cation with a positive charge of 1. So we have 1 positive charge on the potassium, and we have 1 negative charge on the chlorine. Our second example, we're going to look at magnesium combining with chlorine. Now magnesium, we look it up on the periodic table. Magnesium is in the second group of the periodic table, so it has 2 valence electrons that it needs to give up. I apologize for the little flip-flop there. So magnesium needs to give up 2 electrons. Chlorine can only accept 1. So we need another negative on the anion side. So what we're going to do is put a little 2 down by the Cl. And now we have a balanced charge. You take the 2 times negative 1. We have 2 negative 1s. And we have 2 positives. Positive 2 plus negative 2 equals 0. Our combined ions become neutral. All the electrons are accounted for. Covalent formulas. Covalent formulas are slightly different in their naming. We are going to use these prefixes from this chart. This chart is in your books. It will tell us, based on the prefix, how many of each atom we have. Now carbon dioxide will be the first one we're going to look at here. Carbon is at the beginning, so we will not use the prefix mono. It's just a rule chemists have developed over the years. If there were 2 carbons, we would use the prefix di. So we'd have dicarbon dioxide. In this case, though, we only have 1, so we have carbon dioxide. So we're going to use that prefix di on the oxygen, and we're going to look it up on the chart and find out that there are 2 oxygen atoms in this molecule. So we're going to put a little 2 to tell us how many oxygens we have. CO2, carbon dioxide. If we were to name something like carbon monoxide, it would have 1 oxygen, CO. Water, H2O, is a covalently bonded compound. Its formal name, most of the time chemists just call it water, but the technical name for it would be dihydrogen monoxide. 2 hydrogens, dihydrogen monoxide, meaning 1. Now, the oxide is still going to be called an oxide. I know it is not an anion, but we are still going to use the IDE suffix on the oxygen, the fluorines, the bromines, etc., etc. Thanks for tuning in. I will see you in class.